Good day everyone, I'm Jia and I'll be sharing on my final year project, Self-Evolving Neural Fuzzy System with Application in Portfolio Management. This will be the outline of the presentation. A quick introduction on deep learning. Deep learning is a machine learning technique that uses multi-layer neural networks to learn the features of the raw input data to solve problems such as image classification and time series prediction. However, deep learning model is often regarded as a black box, where even experts face difficulties in explaining what's going on between the layers and how the predictions are derived. There is a trade-off between interpretability and prediction accuracy. Although deep neural networks gives good performance, it is hardly understandable to humans. In addition to the low transparency of the model, concept drift is an issue, and the volatile nature of stock prices makes it difficult to make accurate predictions. When concept drifts occur, conventional offline modeling techniques are unable to adapt to new patterns in the data. Therefore, this project aims to improve the interpretability of the deep neural network by introducing fuzzy logic, which is an approach that allows a more human way of decision-making reasoning, and its adaptability to handle dynamic input data stream by introducing an incremental learning technique that allows the model to learn incrementally from new information. The model will be applied to financial stock dataset to evaluate the prediction accuracy of future stock prices, and subsequently, the forecasted stock prices will be integrated into our proposed trading strategy, and the portfolio performance will be evaluated under different market conditions. Moving on to our proposed architecture, there are a total of 5 main layers. The first layer, input layer, takes in the input data with each node representing an individual feature of the input data, and it will transmit the crisp input values to the next layer. In the second layer, the condition layer fuzzifies the data by clustering the input features using dense stream, which is an incremental clustering algorithm that can handle concept drift. After fuzzification, this output of layer 2 will be fed as the input to layer 3. Layer 3 consists of two components, the LSTM component, which is a deep learning model to perform supervised learning tasks with the fuzzified membership value. The output of the LSTM network forms the consequence of the fuzzy rules, which is connected to the fuzzy rule base. And in the fuzzy rule base, it maintains a set of rules induced from layer 2 as antecedents and layer 4 as consequence, which is used for the inference process. In layer 4, the consequent layer consists of the fuzzified values of the output features using dense stream, similar to the condition layer. Lastly, in layer 5, defuzzification is performed on the output to obtain the crisp value by using center of area defuzzification method. The dataset chosen for this project is S&P 500 from 1993 to 2020. In this project, we use a sliding window normalization to better reflect the changes of the new data point relative to more recent data points. Next, we performed feature selection to identify the most important features that contribute to the predictive power of the model. This is done by using Monte Carlo evaluative selection technique. Lastly, we use downstream local clustering to cluster our input and output features. The clusters formed are then used to generate the membership degree to define our fuzzy sets. These are the results for different predicted days from 1-day look ahead to 5 days look ahead. We can observe that the model performed well for look ahead day of t plus 1 with a relatively high R-squared score of 0.975, and the performance of the model seems to drop as we attempt to predict further look ahead days. Ideally, we would like to sell a stock when it's at its peak and re-enter the position at its trough to make a profit. In this project, we will be looking at MACD technical indicator to identify the trend and momentum of a stock. As shown in the diagram on the right, whenever the blue MACD line crosses above the red signal line, it indicates a bullish signal, and whenever the blue MACD line crosses below the red signal line, it indicates a bearish signal. This crossover can help to identify a potential reversal in the market trend. However, MACD is a lagging indicator which inhibits the ability to make the best trading decisions if it misses the peak point. The image on the right is a comparison of the different types of MACD. Firstly, we have the perfect look ahead MACD, which uses the hindsight values and essentially removes the time lag present. Next in line, we have the vanilla MACD without any forecasted or hindsight values, resulting in a significant delay in the crossovers. Lastly, we have the proposed forecasted MACD, where we integrate the forecasted price of t plus 1 in our previous experiment to reduce the time lag present and bring the crossover points closer to that of the perfect look-ahead MACD. For the experiment setup, the starting capital is fixed at $100,000 with a commission fee of 0.1% per trade executed. In this trading experiment, the performance of three strategies, namely the buy and hold strategy, the vanilla MACD strategy, and a proposed forecasted MACD strategy, will be evaluated under different market conditions. First up, we have the bull market, and we can observe that the buy and hold method performed the best with the highest return of 73.49%. For the bear market, our proposed forecasted MACD performed the best with a positive return of 4.63%. And for the volatile market, our proposed forecasted MACD performed the best with the highest return of 8.17%. In conclusion, we have implemented a system to introduce interpretability to the deep neural network and its adaptability to concept drift by using downstream algorithm. Our model managed to forecast stock price for S&P 500 data and achieve a high R-squared score of above 0.9 for up to 5 days look ahead. Our proposed trading strategy result was also promising and outperforms two other trading strategies under different market conditions. For future work, the implementation of genetic algorithm can be considered for optimal hyperparameter tunings. Other technical indicators can be experimented and used together with the proposed method to achieve better results. And lastly, future work can look at portfolio rebalancing to manage a basket of assets in the portfolio and reallocates the resources based on the asset's performance. And this concludes my presentation. Thank you.